Good afternoon, class. Today we'll discuss the end of Chapter 6, Section 6.5, which talks about approximating a binomial distribution using a normal distribution. So in Section 5.2, remember that we learned to use the binomial formula shown here to calculate binomial probabilities. Let's first recall the properties of a binomial distribution. So remember that the probability experiment consists of a fixed number of trials we denote by the letter n. Each trial is independent of the others, and remember that we say two events are independent if one event happening does not influence the probability of the other event happening. For each trial, there are only two possible outcomes, and for counting purposes, one outcome we label a success and the other a failure. And finally, for every trial, the probability of getting a success is denoted by the letter P, and the probability of getting a failure is denoted by the letter, by 1 minus B. So let's look at an example. After forgetting to study for your statistics test, you believe that you only have a 25% probability of answering any given question correctly. Your test includes 50 true-false questions. Assuming that your estimate is the true probability that you will answer a question correctly, find the probability that you will miss no more than half of the questions. Now, we begin by noticing that answering the test questions correctly is binomial, since you are either correct or incorrect in your answer. If a trial is a single question on the test, then we have n equals 50 trials for this problem. Now we will define our discrete random variable as x. Remember from chapter 5, we use this capital X, and it counts the number of successes. So x will represent, in this case, the number of questions marked incorrect, since we are asked in the problem about missing questions on the test. So finally, we want to calculate the probability that x is less than or equal to 25. And that's because we will miss no more than half of the questions here. So half of the questions are, half of 50 is 25, and no more is equivalent to the mathematical statement less than or equal to. Now, the problem arises because when we look at this probability, because each event is mutually exclusive, using section 4.2 and our addition rule for probability, we can sum each of the probabilities, because this is really an or statement. X is less than or equal to 25 means x is 25, or, so we sum, x is 24, or x is 23, so forth, all the way down to or x is 0. This would mean that we would have to calculate 26 individual probabilities for this problem. It turns out that we can use the normal distribution to approximate this binomial probability. If the conditions that n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10 are met for a given binomial distribution, then a normal distribution can be used to approximate the normal probability distribution, the binomial probability distribution with the mean and standard deviation given by mu equals n times p, and sigma is the square root of n times p times 1 minus p. Remember that these were formulas that showed up on your exam 2 formula sheet, and therefore they will continue to show up on your exam 3 formula sheet. And this is where n is the number of trials, p is the probability of getting a success. Well, let's note the condition n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10 ensures that the graph of the binomial distribution, which we in fact call a histogram, this is just a nice way of saying a bar graph in our statistics course, is symmetric about its mean as seen below here. So when we satisfy these criteria, our bar graph is symmetric and we can approximate it using a continuous normal curve. Now, we are trying to use the normal distribution, which remember is continuous, to approximate the binomial distribution, which we saw in chapter 5 was a discrete distribution. So a continuity correction must be used to convert the whole number value of the discrete binomial random variable to an interval range of the continuous normal random variable. A continuity correction is a correction factor used to convert a value of a discrete random variable to an interval range of a continuous random variable when using a continuous distribution to approximate a discrete distribution. Now, the trick we will use for this section to make this continuity correction, we determine the value x of the binomial random variable, and we will convert it to the interval x minus 0.5 to x plus 0.5. So if we have a single point representing our discrete value from our binomial distribution on the number line, what we're going to do is we're going to subtract 0.5 and add 0.5 to create this interval range around x. Now let's look at an example. Use the continuity correction factor to describe the area under the normal curve that approximates the probability that at least 2 people in a statistics class of 50 students regularly cheat on their math tests. Assume that the number of people in a statistics class of 50 students who consistently cheat on their math tests has a binomial distribution with a mean of 5.00 and a standard deviation of approximately 2.12. Now notice for this problem, we would like to calculate the probability that x is greater than or equal to 2, where x is the binomial discrete random variable that counts the number of students who cheat, because this is what we're interested in the problem. So this is what we're going to label as a success. And remember that the word at least is equivalent to the mathematical notation greater than or equal to. We now convert the discrete value 2 into an interval by adding 0.5 and subtracting 0.5 from the number 2. So our single value 2 now turns into the interval range 1.5 to 2.5. So it contains all of the numbers between 1.5 and 2.5. Next, we shade the area corresponding to the phrase at least 2. This would be the area under the curve for x values greater than or equal to 2. Therefore, the area, sorry, this is another typo, the area corresponding to at least 2 would include the interval 1.5 to 2.5. Because our statement includes 2, we include the interval range. So if it includes the discrete value, we include the interval range. And all x values to the right of 2.5. So we can see this picture. Here's our value 2. We've now turned it into an interval range. Since we include 2 and everything above 2, we're going to now also include the interval. So the area is all of the area to the right of not only 2, but to the right of 1.5. So this is the area under the normal curve with a mean of 5.00 and a standard deviation of 2.12 that approximates the probability that at least 2 people in the statistics class regularly cheat on their math tests. You can take a glance at this. You can download these lecture notes and take a look at this. It gives you hints on how to use the continuity correction for different setups and different types of problems. But let's now return to our original example. So remember that we had the problem after forgetting to study for your statistics class test. You believe that you only have a 25% probability of answering any given question correctly. Your test includes 50 true-false questions. Assuming that your estimate is the true probability that you will answer a question correctly, find the probability that you will miss no more than half of the questions. Now recall that we would like to calculate the following probability. The probability that x is less than or equal to 25. And this is where x counts the number of incorrect questions you received on your statistics test. Now we first use the continuity correction to convert our discrete value 25 from the probability statement. So our single value 25, remember what we do is we both add and subtract 0.5. So our value 25 turns into the interval range 24.5 to 25.5. Now, since 25 is included in our probability statement, we will include the entire interval 24.5 to 25.5 in our new continuous probability statement. This means that we are now interested in the area to the left of the value 25.5. Now, think about this for a second. Do you see why this is? If not, perhaps send me an email. Now, to finish the problem, we need our mean and standard deviation of the normal distribution used to approximate our given binomial. Since the success is missing a question, and you have a 25% chance of getting a question right, then you have a 75% chance of missing a question. So our probability of success, which in this case is missing a problem, is 0.75. So therefore, our mean, mu, remember that mu is given by n times p. This is just the mean of a binomial. And so we get 50 times 0.75, which gives us 37.5. And our sigma is this square root statement, and we get approximately 3.061862. Now, we can use either our statistical tables to find this probability statement by first standardizing our value 25.5 and converting it to a z-score, or we can utilize our graphing calculator as we have seen in section 6.3. The final result that you should get is 0.0000. Again, if you have any questions on this material or any other material from Chapter 6, please send me an email or post in our Chapter 6 discussion board.